All right, so this is section 4.7 of Math 146. This section, we're going to talk about the sum and difference formulas of our trigonometric functions, sine, cosine, and tangent. I will be completely honest when I tell you that I know the sine and cosine ones very well because I've used them. The tangent one, not so much. As a matter of fact, I've almost never memorized the tangent one, and there are alternative ways you could actually do the tangent one when we get to it. But I'm going to supply the formula for you. Just know that you'll use the tangent one here for some of these problems, but I will personally not test you on the tangent one again, just because I don't find them quite as useful as the sine and cosine ones. So let's go ahead and get started. I would love to say that I'm going to go through the proofs of why all these things work. That would unfortunately make these what takes already long videos even longer, and I don't want to go through that. So there are certainly proofs you could look up for this stuff if you really want to know. We will do a little bit of verification, but I'm not going to actually do the proofs of how and why this works. So like I said, there are what's called the sum and difference formulas for sine, cosine, and tangent. So I'm going to start off with the sine one. And what does that mean by sum and difference formulas? Well, the idea is that if I were to take the sine of some angle plus another angle, so alpha plus beta, that is going to be equivalent to the sine of alpha times the cosine of beta. Let's make that actually look like a beta, plus the cosine of alpha times the sine of beta. And then if I were to do the subtraction, the difference formula of alpha minus beta, that is going to be the sine of alpha cosine of beta minus cosine of alpha sine of beta. So that's the ones for your sine function. There's a shorter way to write this, and this is going to be useful when it comes to the next two. So this is the only time I'm going to split them up. If I want to do the sine of alpha plus or minus beta, so the key there is the way I wrote that plus or minus. We've pretty much all seen that kind of thing before. Well, that will be the sine of alpha cosine of beta plus or minus cosine of alpha sine of beta. And the reason that this is important is because the way I wrote this, what you should be able to see is that on top here is the plus, and on top here is the plus. So if I have plus for sine, as you could see in the one above, then I've got a plus over here. And then the bottom piece is the minus, so that if you have a minus, then you've got a minus over here. So this is probably the better one to go from, just because it's a little more compact and you don't have to memorize both of them. Just know that whatever the sign is on the inside of the parentheses, as far as positive and negative sign, it's going to match the positive or negative sign that you have for your formula on the right. So now if I want to do cosine, I'm going to shorten that to cosine of alpha plus or minus beta. And the cosine equation, just a little bit different in the fact that you're not multiplying a sine and a cosine together. It's going to be cosine of alpha cosine of beta. And then here's the big issue here. When when you have two angles added on the left, you are actually going to subtract on the right. And when you have two angles subtracted on the left, you are going to add on the right. So instead of a plus over minus, it's a minus over plus. It just tells you that the signs here, the positive and negative signs, are going to switch for cosine. And then it's going to be sine of alpha, sine of beta being multiplied over here. So a gentleman that I used to work with a long time ago made up this little routine. Well, I don't know if he made it up, but He used to do this little routine that was kind of a like a cheerleading routine, which I will not do, but basically the little saying that he said um, used to, it still actually rings true to me. It's for sine, it's sine, cosine, cosine, sine, and then for cosine, it's cosine, cosine, sine, 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 meaning that middle piece right here means you flip the signs. So it's sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. Again, if I was going to do the entire little routine here, that would be quite hilarious, I'm sure, but I'm not going to do that. Anyway, it's whatever you come up with to remember these things. So the sine one is a multiplication of sine and cosine, and it's the same sign as far as positive and negatives, and then you're going to multiply the cosine and the sine of the other two angles. For the cosine one, the order is important as far as the subtraction here. It's cosine of one angle, cosine of the other angle, and then you flip whatever the sine is, and then it's the sine of the two angles multiplied together. And then tangent. Again, this is the one that I have actually never memorized. I probably memorized it at once when I was in school, and that's probably about it. Tangent of alpha plus or minus beta. So the formula is tangent of alpha plus or minus tangent of beta. So you can see that the signs here, the positive and negative signs, are going to stay the same on top. And then on the denominator, it's going to be 1 minus over plus tangent of alpha, tangent of beta. So the sign in the denominator switches. That is definitely one of the more complicated ones to learn. Now, the reason I said that there's another way to do this is because if you understand that tangent is sine divided by cosine, technically, if you wanted to find the tangent of alpha plus beta, you could do the sine of alpha plus beta over the cosine of alpha plus beta, and you're going to get the same result. Believe it or not, they do actually simplify to this little equation right here. So you can pick and choose whichever way you want to do it, whatever works best for you. So why is it that we kind of need something like this? Well, to kind of show this, again, this is not a proof. This is just going to be showing that this works. Let's do an angle that we already happen to know. So what we should know is the sine, and I'm going to use degrees in here, but it'll just make it easier for us to look at. We should know that we should know what the sine of 30 is, and we should know what the sine of 60 is. So literally, if you were to add 30 and 60, you would get that that equals the sine of 90 degrees. And of course, the sine of 90 degrees is the same place as the sine of pi halves, which is 1. So if we were to now utilize our formula, the formula says that this is going to be the same thing as the sine of 30 times the cosine of 60 plus the cosine of 30 times the sine of 60. Okay, the sine of 30 degrees is 1/2. The cosine of 60 degrees is 1/2. Plus the cosine of 30 degrees is the square root of 3 over 2. And the sine of 60 degrees is the square root of 3 over 2. So now simplifying, you get 1/4 here. Simplifying over there, square root of 3 times square root of 3 on top is 3 over 4. 1/4 plus 3/4 is indeed 1. Okay, and that's really the only time I'm going to show that this actually works. And the reason that I showed this one is because we happen to already know what 30, 60, and 90 are for sine and cosine. So those were known values based upon unit circle stuff. So the reason that we actually do something like this is because maybe we have to try and find the sine or the cosine of some angle that is not part of the normal unit circle, but we can use unit circle values to do it. So our first actual example is, let's say that we want to find the cosine of 75 degrees in its exact form. Okay, obviously you could plug cosine of 75 degrees in your calculator in degree mode and it'll spit out some decimal approximation, which is a good approximation, but it's not going to be the exact value that we're looking for. So in order to do that, we're going to use the cosine and we're going to use a different sum or a difference formula. So you have to figure out what makes the most sense. What things can I either add up to 75 or subtract to get 75 based upon actual unit circle angles that we already know. And 75 is typically not too difficult of one because you could use 30 and 45, both of which are unit circle values, and we can add those up. So this is the same thing as saying the cosine of 30 plus 45. Okay, that should make sense. Well, now you can use the cosine sum formula, which is cosine of the first angle, cosine of the second angle. Cosine flips its sign, so that would be minus sine of the first angle, sine of the second angle. And now we can evaluate. Now you do have to know, again, you have to know all your unit circle stuff to do this. So cosine of 30 degrees is square root of 3 over 2. Cosine of 45 degrees is root 2 over 2. Minus sine of 30 degrees is 1/2. Sine of 45 degrees is, again, root 2 over 2. So simplifying, now on the left-hand side here, we've got square root of 3 times square root of 2, which becomes the square root of 6 over 4 there. And then that one's going to give us the square root of 2 over 4. So combining the two fractions, we get root 6 minus root 2 over 4. And that is an exact answer for the cosine of 75 degrees. Again, you could do a decimal approximation afterwards, which should give you the same thing as if you were to plug cosine of 75 degrees into your calculator, but that is the exact value. Okay, so now let's do one, we'll stick with cosine for now, but let's do one that is in radians. So let's say we want to find the exact value of cosine of pi 12. Well, considering that pi over 12 is definitely less than pi over 3 and pi over 4 and pi over 6, I'm probably going to have to use a subtraction formula of two known values to get there. And you may have to do a little playing with this to figure it out. But you want to figure out, in terms of twelfths, what things can I subtract to give me twelfths? But then when I reduce them, they're going to be known values. And again, you may have to play with it a little bit, but if you do 3 pi twelfths, which reduces to pi over 4, we know pi over 4, minus 2 pi twelfths, which reduces to pi over 6, we know pi over 6, then we can use this. So I'm going to rewrite that as pi fourths minus pi sixths. All this is doing is setting up the fact now that we can use the difference formula for cosine. So again, it would be cosine of the first angle, cosine of the second angle, and since it's a minus, since we're doing a subtraction, this one becomes plus, and then it would be sine of the first angle, sine of the second angle. And again, we know all these values. So cosine of pi fourths is root 2 over 2. Cosine of pi sixths is root 3 over 2. Plus sine of pi fourths is root 2 over 2. Sine of pi sixths is 1/2. So on the first one, we get root 6 over 4. And on the second one, we get root 2 over 4. Combining those two, we get root 6 plus root 2 over 4. Very similar to the answer that we just got prior to this, but this one was plus on top instead of minus. There may be patterns that you can figure out for some of this stuff, and if you do, more power to you, but it's still better off just to go ahead and go through this process and show how the work is done. All right, so again, I am not going to walk through this process, although it is kind of neat, but this is the same process that you could use if you wanted to prove the identity, cosine of pi halves minus theta is the same thing as sine of theta, which ultimately just says that cosine and sine are shifted by pi halves of each other, or vice versa. Sine of pi halves minus theta, pi halves minus theta is the same thing as cosine of theta. Again, that just proves that they are, again, shifted functions of each other by pi halves. You can go ahead and do that if you would like to. It's not a bad little thing to try and prove using the sum and difference formulas. But I'm not going to walk through that again. It would take a little too much time. So now let's try and use the sum and difference formulas to do something for sine, and then we'll do some stuff for tangent and do some identity proving. So let's do an example. Let's say we want to find the exact value of sine of 7 pi twelfths. So again, you have to think of what things can I either add or subtract to get to 7 pi twelfths. Well, 3 and 4 seem to be the easiest things to think of. 3 pi twelfths and 4 pi twelfths. And why is that good? Because 3 over 12 reduces to the 1/4, so you have pi fourths. 4 over 12 reduces to the pi thirds. So you're going to get a pi fourths and a pi thirds as your angles. So pi fourths plus pi thirds, and both of those are special unit circle value angles, so we can go ahead and do this. So sine is sine of the first angle, cosine of the second angle, and sine keeps its sign, so that's going to be a plus, and then you flip it, so then it's cosine of the first angle, sine of the second angle. And then we can evaluate. So let's see, sine of pi fourths is root 2 over 2. Cosine of pi thirds is 1/2. Cosine of pi fourths, root 2 over 2. Sine of pi thirds, root 3 over 2. So the first one is going to give us root 2 over 4. The second one, root 6 over 4. Adding those together, root 2 plus root 6 over 4. And I am sure you're probably starting to pick up on the fact that we've got a lot of root 2s, root 6s, and 4s in this thing. That is relatively common for the ones that we're dealing with. Not always going to be the case as far as what the values are, but since we're trying to use unit circle values to do this, that's going to be relatively common. All right, so instead of doing another one that looks just the same as this, why don't we take the process and go backwards a little bit? Let's say we want to find the exact value, but what we are given is sine of 80 degrees times cosine of 20 degrees minus cosine of 20 degrees sine of 80 degrees. So what you would have to notice here is that, oh, this is already the expanded form of sine, and it's a minus sign in the middle, so this is the difference formula for sine. So ultimately what that's saying is, okay, well, if I've got my two angles, I know it's going to be sine of the first angle minus the second angle. That's what that formula was. We're just going backwards. And of course, that's going to give us the sine of 60 degrees, which just happens to be 1 on the unit circle that we know, and the sine of 60 degrees is root 3 over 2. So that would be the exact value, given the fact that that was already in its expanded form. So we just had to take the process backwards. All right, so let's do an example where we're given some known information. We're actually told what the sine of alpha is. We're told that the sine of alpha is 4/5. We are also told that alpha, oops, got my inequality symbol, alpha is going to lie in between pi halves and pi. Okay, so that pretty much tells us that alpha itself is going to be in the second quadrant. And we're also told that the sine of beta is -2 over root 5, and beta is going to lie in between pi and 3 pi halves, which tells us that beta is in the third quadrant. Okay, so you kind of have to pick up on that. So what this means is quadrant 2. This is telling us quadrant 3. So I've got two pieces of information here about sine. I've got sine of alpha and sine of beta. Well, let's say, and I'm not going to do all these different examples because there's all kinds of different things you could do, but let's say we want to find the cosine of alpha. Let's do cosine of alpha plus beta. There we go, cosine of alpha plus beta. Well, in order to do cosine of alpha plus beta, first of all, you should write the formula out. Cosine of alpha plus beta. So this is cosine. It's going to be cosine alpha, cosine beta. The sign is plus in there, so we switch it. It's minus sine alpha, sine beta. Well, from the given information, I have sine of alpha and sine of beta. So literally, I can just plug that and that in for these two things right here. That's not a problem. The problem is the fact that we don't know what the cosine of these things are. We weren't given that information. So in order to do this, you basically need to set up a couple of right triangles because we need to figure out the cosine of these angles. And since we actually don't know what the angle is, the best way to do it is to set up right triangles. And we're going to label that alpha. And on this right triangle, we're going to label that angle beta because these are different triangles, different angles. So let's see, from what the given information is and the fact that we know we've got alpha, it says sine of alpha is 4/5. Well, sine is the opposite over hypotenuse. So that tells me that that's 4 and that's 5. And if you use the Pythagorean theorem to find the missing side, that's 3. I'm not walking through the Pythagorean theorem there, but that's how you would get that. Might have to do a little bit more work with it with the beta part. Once again, they tell us the sign. In this case, it's negative, but don't worry about the positive and negative just yet. We're going to come back to that. But we know the opposite side would be 2. The hypotenuse would be root 5. So let's see, using the Pythagorean theorem, if we square the hypotenuse, that's going to give us 5. If we square the right leg over in there, in that case, that's going to be 4. So 5 minus 4 is 1. Taking the square root of that is also 1. So I'll write that in green, actually. So that's going to be a 1. And the reason that that's important is because now it allows me to find the cosine of each one of these things. So I know now that the cosine of alpha, based upon this right triangle, is adjacent 3 over hypotenuse 5. And that the cosine of beta, based upon the second triangle, is adjacent 1 over hypotenuse root 5. Now I have everything that we need to go ahead and plug into our formula to find the value of cosine of alpha plus beta. So let's see. I'm trying to keep all this on the screen at the same time here. So, cosine of alpha. First of all, we know from the top information that alpha lies in between pi halves and pi. Cosine in the second quadrant is negative. So really, cosine of alpha should be a negative 3/5. And then beta, we know, lies in between pi and 3 pi halves, which is third quadrant. Once again, cosine is negative there, so we'll throw our negative out in front. So that's how we take care of that. You don't have to like draw the triangles in any specific way. You just have to remember to go back to where is this thing located and know based upon that what your trig function signs are going to be. So now we can do this. Cosine of alpha is negative 3/5. Cosine of beta, negative 1 over root 5, minus Sine of alpha, that was given to us, that's 4/5. Sine of beta, that is -2 over root 5. And now simplifying, we get +3 over 5 root 5 plus, because I got a minus minus there, 8 over 5 root 5, which is going to give us 11 over 5 root 5. Okay, and that is a perfectly legitimate and acceptable answer. If we need to rationalize, which we certainly can, you would multiply the top and the bottom by a square root of 5, which would give me 11 root 5 over 5 times 5, which is 25. So 11 root 5 over 25 would probably be the most simplified answer for this one. Okay, it's not a short problem to do, but it is a good problem to do. All right, we're gonna stop this video here. This will definitely be a 2-video lesson because there's a lot of stuff. We'll, like I said, we'll come back. We'll do some establishing some identities or identity proofs, and then we're going to do a couple of things with tangent, but not too much with it. And then we'll do some solving. So we'll get all that stuff done in the next video.